Okay, so this graph for chemical equilibrium is what we were talking about yesterday, but I wanted you to see and make sure you understand the concept that just because at equilibrium the forward and the reverse rate are equal, that it's not necessarily that they have the same concentrations. So I wanted you to see the first one, which is showing the rates become equal at when equilibrium is reached, and that when you reach equilibrium, you're not really changing the amounts of the concentrations, but yet they're not necessarily equal concentrations. So in this case, we have more products than reactants when we've reached equilibrium. So would we expect our K value for this particular graph to be greater than 1 or less than 1? Greater than 1, because when it's greater than 1, it favors the products. So this would be like where equilibrium is basically achieved, and you see that there's no overall change once it's achieved. Okay? But today what we're going to be talking about is we're going to be talking about systems that have reached equilibrium, and then we change a parameter in them, or we stress the system, and then the equilibrium will shift to relieve that stress. Okay? So it's called the Châtelier principle, and we're going to talk about shifting left, shifting right, or no shift, because sometimes it won't have an effect. So when a system experiences stress, the equilibrium will shift to relieve that stress. Okay? So factors that will cause the shift is changes in pressure, changes in concentration, and temperature changes. When we're referring to changes in pressure, we are only talking about gases, because that's the only thing that will affect pressure is a gas, or gas other way around. Sorry about that. Pressures will only affect gases, not liquids and solids. It doesn't matter because we're not putting liquids and solids in our equilibrium constant, are we? No, we are not. Concentration changes and temperature changes. When concentration changes, we're going to I put in parentheses volume changes in there, because when I change the volume of a gas, I change the concentration, do I not? So if I had a container and I make it smaller, what happened to my concentration of gas particles? It increased. So that's why that's kind of falling under there. You can also sometimes do volume with pressure, because they are what? How are pressure and volume related? Inversely. So if I increase the pressure, I decrease the volume, which would also affect the concentration. So really, both of those could go back to concentration. Okay? All right. How will the system shift? Due to pressure changes. Okay? So if we're looking at this particular equation, we see that they have unequal moles on each side. So the reactant side has 4 moles of gas. The product side has 2 moles of gas. That is very important when we're looking at pressure changes, because it's going to either shift toward the side with fewer moles or toward the side with more moles, depending on what you're doing to the pressure. If it's equal number of moles, let's say I had 2 moles on both sides, reactants and products, there would be no shift. But if it's unequal, if I increase the pressure, I'm basically increasing the concentration. So it would shift toward the side with fewer moles. So if for this particular system, if I increased the pressure, the reaction equilibrium position would shift to the right, creating more ammonia. Okay? But if I were to decrease the pressure, it would shift towards the sides with more moles. Okay? If I change the pressure by adding a noble gas or an inert gas, it has no effect. Okay? It will not affect the equilibrium constant. Okay? The noble gas or inert gas, the same thing, have no change on the system at all. Okay? No change. Now, changing the pressure might affect the equilibrium position, but it will not affect the overall constant. It just causes it to shift until equilibrium is reestablished. So if I talk about this and I say I'm going to increase the pressure, I would shift my reaction to make more product, but ultimately it would reach equilibrium again and still have that same equilibrium constant. So by making these changes in pressure, I'm not affecting the overall constant. I just cause the reaction to shift until reestablish equilibrium. Okay, I want to make sure I understand that. Okay, so let's look at these and we're going to say whether they shift left or shift right, or no shift. Okay, so in this particular case, it's asking if I'm increasing the pressure on these 3 systems, what is going to happen to the equilibrium position? How will they change to reestablish equilibrium? So how will the first one change? It would be no shift, because there are equal number of moles on both sides of the equation. Okay. The next one is 3 moles of reactant forming 2 moles of product. So if I increase the pressure, what's going to happen to my position? How will it shift? It's going to shift right. Because it's going to shift towards the side with fewer moles. In the next equation, I basically reversed the previous one. So now I have 2 moles of reactants and 3 moles of product. So if I increase the pressure for this system, which way would it shift? Left. Correct. Shift left. All right. So any questions on pressure? So now let's talk about concentration. So there we have this reaction, A plus B yields C plus D. Increasing the concentration of any one of those species will cause a shift away from it. So whether I have a reactant or product, if I increase A or B, it's going to shift away from that and start making more product. So it would shift to the right. If I were to increase C or D, it's going to shift away from that, so it would shift back towards the reactants or to the left. Okay? So that's if I'm increasing the concentration. It shifts away from it. Okay? What if so I just write this, increased, shifts away. But I mean, it depends on where I'm increasing. Just know, increase shifts away from it. So what would the opposite of that be? If I decrease the concentration, so let's say I decrease the concentration of A, what's going to happen to my shift? It'll shift toward it, so then I would increase it to the left. So if I'm increasing, it shifts away. If I'm decreasing, it shifts toward it. Okay? One way that it will often show decreasing is instead of saying it decreased the concentration, it might say I removed some of one of the reactants or products. And so removing it is decreasing it. Okay? So if in this case, it's saying if I increase to A or B, it's going to shift away from it, so it's going to go to the right. If I increase C or D, it's going to shift away from it, so it would shift back to the left. But we need to know the opposite. We need to know if I'm decreasing, it'll shift toward it. Okay? So far, so good? That's what I just said. I get ahead of myself. It shifts towards it. When I am changing the concentration, however, you do need to know that it is not affecting the equilibrium constant. Okay? When we're talking about these shifts, we're talking about shifting until equilibrium is reestablished. So if I increase the concentration of A or B, it shifts to the right and starts making C or D. Well, when I plug those new numbers into my equilibrium constant expression, guess what? I'm decreasing one, increasing the other by the same amount, so it comes out to be the same equilibrium constant. All right, so if I have these two particular ones, if I am increasing, for this one I have ammonia, I'm producing ammonia, and it says I condense the ammonia and remove the ammonia from the system. So I'm decreasing the concentration of ammonia, right? If I'm removing it, I'm decreasing, like I'm taking it out of the system. So what's going to happen to this reaction? Which way will it shift? Right. Shift right. So that means more NH3 would be produced. What about the next one? I am increasing the concentration of HCl. So this one I'm increasing. What happens when I increase the concentration? It shifts to the left. It shifts away from it to the right. So that means more products would be produced when I did that. Any questions on that? Does it make sense mostly? Okay. What about temperature? How is temperature going to affect that? Usually students find temperature the trickiest. Okay. This is going to sound confusing. I'm going to tell you an easier way to remember this, but I got to tell you this way first. Okay? Oops, too far. Sorry. Okay. So reversible reactions are endothermic in one direction, exothermic in the other. And when we reverse them, they're the opposite. We already know that from the last unit. So depending on if its forward reaction is endothermic, then the reverse reaction would be exothermic. Okay? When the temperature is increased, the equilibrium must shift so that the reaction is running in the endothermic reaction. When it's decreased, we want to run it in the exothermic reaction. That's confusing. I'm going to tell you a better way to do it, okay? Because I actually don't like the way that's worded. It's technically what's right, but technically I have a better way for you to remember it, okay? When we have an exothermic reaction, it looks like this, okay? We treat our heat as a product. Add that in your notes. You can write it right above the reaction. Treat heat as a product. So in an exothermic reaction, if we're treating heat as a product, what are we going to treat endothermic reaction as? As a reactant. Okay? So if we are treating these things as a reactant or a product, we can go to that whole thing of if I increase it, it shifts away from it, right? So if I'm increasing the concentration of my heat, it would shift away from it, right? So in the case of an exothermic reaction, if I increase the temperature, so let's look at this particular one. If I increase the temperature of that reaction, which way is that going to shift? To the left. It's going to shift away from it. But if that same reaction, I decrease the temperature, so I'm removing heat, which way would that first reaction shift? To the right, towards it. So it's much easier to treat it that way than that confusing sentence of make sure it's going in the endo. Treat it as a reactant or as a product. So let's look at the endothermic one. Now we have heat as a reactant. If I increase the temperature, which way would that reaction shift? Right. So if I'm increasing, whoops, oh well, I need that on there. So in this case, if I increase, it's going to shift away from it, so it would produce more product. Okay? Let's think about what an endothermic reaction is. What do we have to add to an endothermic reaction to get it to happen? Heat. This makes perfect sense. If I increase the heat of an endothermic reaction, it's going to proceed to make more products, right? Because this is the whole purpose of an endothermic reaction. It needs energy to happen. So it kind of makes sense. Not kind of. It really makes sense. Now, this is the only thing that will affect the equilibrium constant. Change in temperature. It will change your constant. Okay? Which kind of makes sense again if you go back to that equilibrium expression of products over reactants. I'm not changing any of the concentrations of the things, whatever side my heat is on. So like in that endothermic reaction, when I increased my temperature, I started making more product, but I didn't necessarily decrease my concentrations of my reactants. So then my K value is going to go up. Generally, for every 10 degrees that you increase the temperature, your equilibrium constant kind of goes up by a factor of 10, generally. All right, so let's practice this one. All right, so in this first reaction, we have ammonia nitrate dissolving and forming an aqueous solution, and it is an endothermic reaction, right? Because we have a reactant. So would that solution feel hotter or colder when I did that? Colder. Colder, absolutely. Most nitrates, when you dissolve them, are cold. They're cool. Ha ha. Oh. They're cool. All right. So if I increase the temperature, would I basically dissolve more ammonium nitrate or less? More. Because by increasing the temperature on an endothermic, it's going to shift away from it. So it would shift to the right, and so I would actually get more ammonium, which it's asking about. So our ammonium would increase. On the next reaction, we have an exothermic reaction. And this is breaking down, this is actually taking two nitrogen atoms and forming a nitrogen molecule. And it says the temperature is reduced. So if I reduce the temperature, it shifts towards it, right?
Wait, so you get more nitrogen?
So I would produce more N2 because I would shift towards that side. Okay? Does that make sense? All right, that's where we stop. we'll do rice tables on, I don't know if we're doing those on Friday. We might do them next week because y'all have EOC tomorrow.